Okay, so let's go to our second workshop, which will be more about the regression models. And I will first go back to the multiple linear regression, which was be introduced yesterday. So this is the problem that I left for yesterday's workshop in the end. So it will be how to use the multiple predictors to predict the suggested retail price. And yeah, we can use the LM function to do this multiple linear regression, and we can also use the summary function to get the coefficients and the p-values. So let's see how can we do this. So here we will use horsepower, cylinder, CDMPG, and highway MPG. So let's go to R. So, okay, I see more people has come. So this time we will do a multiple linear regression, so we can still use the ARM function. So here, the response is still the suggested retail price. So let me just copy this to reduce some of the typing. Suggest retail price with horsepower and cylinders and city MPG and highway MPG. So you can look at the column names of this data set to make sure that you didn't make any typos when you type these names. And the data will be R04. So this is, it has similar format as the previous simple linear regression model, but we have more predictors, and we will connect these predictors using this plus symbol. And we can also use summary function to get the summary of the model to get the inference. If we run this, we will have the results. So we will know the estimate coefficients for different predictors. For example, the estimate coefficient for CDMPG is 594, and its p-value is 0.05, which is greater than the 0.05 threshold. So here, only two predictors have significant p-values in this case, only horsepower and cylinders. So this is how we run a multiple linear regression model, and you can let me know if you have any questions, and you can also repeat the whole procedure in your site, and you can let me know if you have finished. I will give you maybe 1 minute. Okay, so I will continue. So from these results, we can see that for multiple linear regression, maybe it's possible that some of the predictors do have linear correlation with the response, but some may be not. So it is needed to decide whether each of the predictors is important in this regression or not, one by one, or we have other ways to do hypothesis testings regarding the coefficients. And I will introduce how we do this in the coming slides. And another thing is that how can we check whether these model assumptions are violated? So remember that in multiple linear regression models, we assume that we can write the we can write the yi as the sum of b beta times xi and beta j times xij and with an epsilon. So in this case, the assumption is still about the residuals. So we still assume that the residuals comes from a normal distribution, which is the same for all the observations. So it is needed to check whether this assumption is violated. And I will introduce how to check these assumptions later. So first, let's go back to the least square minimization problem. So as I have introduced in the previous workshop, the key part of the regression model is this the target function to be minimized in the model. In the simple linear regression, we minimize the sum of these square. And in this case, in multiple linear regression, we are still doing minimization for the sum of these square. And this time, there is difference between the previous simple linear regression with this multiple linear regression in terms of these squares, because here, the difference between the true observation and the observed and the estimated expectation will be the difference between yi and sum of bk times xik, where k is from 0 to p minus 1. So this will be the new difference between the estimated value from the regression line and the actual value. So that will be the residuals, and this will be the errors, and this will be the sum of square errors. So this format has is similar compared to the previous one. Okay, and I think we have introduced ANOVA in the previous introduction to statistics workshop. But if you haven't attended that workshop, or if you are not so familiar with ANOVA, I'd like to introduce this again. So ANOVA is short for analysis of variance. So in ANOVA, we want to see whether the variance explained by each part is reasonable from the if null hypothesis is true. So here, the variance can be explained by two parts, which is the variance explained by the regression, which is called SSR, and the variance which is explained by error, which is called SSE. So here, so if we look at the definition of these two terms, the sum of squared regression is the sum of difference between yi hat and y bar. So here, y bar is the average of all the observations. And this difference indicates that if we do not use any regression models, the worst model should be use the average of all the observations to be the predicted value of all the observations, use a constant as the prediction. And this is the worst model, the results from the worst model, and y hat will be the results from our model. So this is the difference between the worst model and our model. And this will explain the part which can be explained by our model. So it is called sum of squared regression. It is how regression improves the model prediction. And the second is called sum of squared error. It is a difference between, sorry, I forgot to add an I here. So it should be yi minus yi hat. And yi hat should be the predicted value for each observation I. And the square of squared error is just this, the yi minus the estimated response from the linear regression model. So it means that from our model, this SSR explains the part which cannot be explained by the model, the random errors. So if a model is good, then SSR should be small because the majority of the randomness can be explained by the model. So SSR will, sorry, I made a mix. So it should be SSE, and yeah, I would do the correction. I would do the correction now, and so that you will not have any confusions. Okay, I will do the correction. Sorry that I didn't check it carefully before. Okay. Okay, I have corrected this. Sorry about my type. Okay, so this is the correct version. So if a regression model is good, then the SSE should be small because most parts can be explained by the model, which is the SSR part. But if a model is bad, and it may not be much better compared to the worst model, which is random guess. And then in that case, if the model is bad, then SSR will be small and SSE will be large. So that's why we take the ratio between these two things as the test statistic to measure whether a model is good or not. And this is intuition of the ANOVA. And the test statistic will be the average. So this here, mean MSR will be the mean squared regression, and MSE should be mean squared error. So this will be the SSR over the degree of freedom, or the SSE over the degree of freedom. So anyway, we want to take the ratio of these two things and make it as the test statistic. So if a good model is good, then SSR will be large, SSE will be small, so that ratio will be large. And in the other hand, if the model is bad, then SSR will be small and SSE will be large, and the statistic will be small. So that is the intuition for the F statistic. So if we compare the original model with, if we compare the model with a random guess, actually this model will have all the coefficients from beta 1 to beta p minus 1. So if we use ANOVA, we are actually looking at whether all the coefficients are 0 or not. If any of the coefficients is not equal to 0, it means that our model is better than a model which has all the coefficients equal to 0. And in this case, the F statistic will be large compared to the null model. And we will do a test for the F statistic, calculate its p-values by comparing it with the null distribution of the SF distribution, and then we will conclude whether the p-values is small or not to make conclusions regarding this null hypothesis. So it is what ANOVA do. And from this, we can see that in ANOVA, we are comparing a model which use all the predictors with a model which use none of the predictors, which is the Y bar here. So the comparison between a null model with a complicated model using all the predictors. So it is treating, the hypothesis is treating all the predicted together. But in sometimes you are maybe not so interested in all the models. You may be interested in one specific predictor. So for example, if we go back to our example, here we will have results for the F test. So we will get the value of the F statistic, and we will get the p-value from this test. So we can see that the p-value is very small, which means that some of the predictors do have linear relationship with the response. But that's not enough, because maybe we are interested in each of the predictors. And that's why we want to do tests for each of these predictors. And this is what this part reflects. So this part will look at one predictor at a time instead of looking at all the predictors at the same time as the F-test did. In this case, for each individual predictor, you will do the similar t-test for that predictor, as we have done for the simple linear regression. So if we go back to the formula, we'll see that the test for beta k is whether this beta k is equal to 0 or not. The null hypothesis is that beta k equals to 0, and the alternative hypothesis is that the beta k not equal to 0. And the test statistic is still the t star, which is the difference between bk and 0 over the SBK, where S is estimate of the variance. So, and then we compare this t statistic with calculate its p-values and compare this p-value with the threshold and get the conclusions about whether this beta k is equal to 0 or not. And let's look at what this test actually means. So when we test whether single beta k equal to 0, it means that we want to test whether the k predictor provide statistically significant improvement to the regression model fit. For example, if we want to test whether beta 3 equal to 0, it actually means that when we already have the first two predictors, x1 and x2, whether adding this third predictor x3 into the model will improve the model prediction, whether it will give some actual linear relationship between this predictor and the response. And we can also test whether several predictors are equal to 0. For example, in this model, if we have 3 predictors, x1, x2, and x3, we can test whether beta 2 and beta 3 are equal to 0. In this case, we are comparing the model which use all 3 predictors with a model which has only 1 predictor. And in this case, we can also use an F test from ANOVA. And here in this F test, we are comparing 2 models. One model only using x1, and one model using all the x1 and x2 and x3. So if the model with all 3 predictors have improvement compared to the previous model, then we say that at least one of beta 2 or beta 3 is not equal to 0. So this may be too abstract here, but I will let you know how we can use ANOVA to do this. Generally, we can use this command line to compare 2 models using ANOVA. So if we make model 1 as the output object of a linear regression model, and model 2 as output from another linear model using a different set of predictors, we can use ANOVA function to compare these 2 models. And I will show how we do this. So if we go back to the previous regression problem, we can so for example, we already have a complicated model which use all these 4 predictors to predict suggest retail price, and we can add another model which only use horsepower to predict the suggested retail price. So in this case, compared to Model 2, the Model 1, the Model 1 has 3 extra predictors: cylinders, CDMPG, and highway MPG. We want to compare these two models to see whether these 3 extra predictors do have improvement compared to the simple model. And we can do this comparison by looking at the output of the ANOVA function. And this is how we do this. So we can see that by doing the F-test from ANOVA, we are comparing these two models, and we can see what's the F-test from this comparison and these p-values. And we can see that the p-value is much smaller than 0.05. So we can see that by adding these 3 extra predictors, this model do have improvement. And we can also do, I will also do an interesting thing that may help you understand what the t-test did. So here I will do another ANOVA using the horsepower, cylinders, and CDMPG. And I will follow.
You're the host, you should be able to mute them.
Yeah, okay, I have done this. Okay. Okay, so here we have a model 3, which is the model having 3 predictors: horsepower, cylinders, and CDMPG. And the missing predictor will be this highway MPG predictor. And we can see that by comparing model 1 and model 3, we have 1 extra predictor, the highway MPG, missing in model 3. And if we do this ANOVA test, we are actually looking at whether we can have improvement in model prediction by adding this 1 predictor. And let's see what happens. We can see that in the second F-test, the p-value from the F-test is 0.46, and it is much larger than 0.05. And it shows that if we already have these 3 predictors, adding highway and PG does not give us extra information. And it makes sense because highway and PG is very similar to city and PG conceptually. And if we already have city and PG, then the information of highway and PG may already be included. So it is reasonable that we don't need this extra information. And if we compare these p-values with our previous t-test, you will see that the t-test for highway and PG is also 0.4679. So we can see that these 2 p-values are exactly the same, which shows that the t-test of this predictor is exactly the same as the results by comparing the model without this predictor and the model with this predictor. And it further confirms confirms the meaning of the single predictor test. It shows that the test for whether beta co-equal to 0 shows whether adding this predictor will provide statistical significant improvement to the regression model. And that's what I would like to say in this comparison. So maybe we can also do the similar ANOVA test on your side, and you can let me know if you have finished. And you can also try different combinations of the predictors to see whether you can have some interesting conclusions. So one thing to be noticed that the order of these models does not matter. So for example, if we ANOVA model 1 and ANOVA model 2 model 1, these two results will be exactly the same. So the order does not matter. And please let me know if you have finished. Okay. Thank you for your response. Okay, and I will continue. So far we have shown how to do different tests concerning the regression coefficients. We can use the f-test to test whether all beta k equal to 0, and we can just use the summary function for the whole regression model to do this. And we have also shown how to test whether a single beta k equal to 0, and it can be done using a t-test for each individual predictor. And then I have also shown whether we can test some of the coefficients are equal to 0. The key point in all tests is that we want to form the full model and the reduced model. The model with all the predictors and the model which is a reduced model and without the predictors that we want to test. And then we can use ANOVA to compare these two models. Okay, yeah, I think I have, yeah, I think, okay, I think we have already done this. Yeah, we use all the, yeah, these predictors to do the prediction to see whether all, we can use the, yeah, we have done this. I think we have done this. So you can use the summary to test whether all the predictors are equal to 0. We can also look at the coefficient for CDMPG by looking at the results of the t-test. And we can also to test, if we want to test CDMPG and highway MPG are zeros, we can just remove these two predictor from the model and do this. Maybe I can just do this actual test. Okay, we have model 4, which has pores, power, and cylinders, and we compare the model 1 with model 4, which do not have CDMPG and highway MPG. And we compare model 1 and model 4. And we can see that for model 4, so for this comparison, it seems that CDMPG and highway MPG do have improvement for the linear regression model fit with a very small p-value. So maybe you can just skip this, as we have already done this. And the next thing will be the diagnosis. So if you still remember, in yesterday's workshop, I introduced how we look at the residual plot and QQ plot to validate the model assumptions. For multiple linear regression, it's very similar to single linear regression. And I will only mention the difference. So first, we can look at, we can do a scatter plot for one single predictor with the response. However, when we are doing multiple linear regression, we will have multiple predictors. And can we still do the scatter plot? Actually, we can use the pairs function on the dataset to get the pairwise scatter plot between the variables. So let's use our class therefore dataset as an example. Or maybe we can use the span dataset as an example. So if we look at the span dataset, we can see that we have 3 columns: height, span, and is.female, which indicates whether this person is female or not. And we can use the pairs function on this dataset to get the pairwise scatter plots. And it will be something look like this. So the first, so this panel will be the scatter plot between height and span, and this will be the scatter plot between height and is.female, and this will be the scatter plot between span and is.female. So this is how we generate scatter plots when we have multiple variables. And you can also try this on your side, and I will also generate some scatter plot for the class therefore dataset, because it may take some data cleaning work. Okay, for example, if you are interested in the scarce retail price, horsepower, cylinders, and CDMPG, will include 4 predictors, and we combine these 4 predictors into a data frame, and we can also do pairwise scatter plot for this one. So maybe you can try this pair function for span, and here I just like to show you what's the scatter plot look like if we look at the class therefore dataset. So you can see in this case we will have also have the pairwise scatter plot for each of the pairs of predictors, and this may give you some intuitions about the relationship between different predictors and the response. So this is how we generate a scatter plot, and we can also look at the pairwise correlations. And this may be something like more numerical. You can use the function called call to calculate the pairwise correlations. And high correlations means that the two variables are highly correlated and highly linear correlated. The linear relationship between these 2 variables are very high, and we can do this in this way. Use call function on class therefore sub, and you will get such a pairwise correlation matrix. And you can also do the pairwise correlation for the span dataset, and you will see, okay, so the correlation between span and height is 0.82, but the correlation between height and is.female is negative 0.5. Yeah, and we can have an idea how correlated different predictors are by looking at these matrices. span only has 3 variables. If there were more, could you specify the variables we want in the plot? Yes, we can specify. So it is what I did for this class 04 data set. So and we can see that for the class 04 data set, we have maybe 10 more than 10. I remember 13 columns, and we can first generate a subset of the whole data set by getting a sub by combining by only selecting several columns of the data frame, and then we only look at the pairwise scatter plot and correlation matrix of that subset instead of the whole matrix. So you'd have to create a subset, but there is no way to do it within the pairs function, right? Yes, I think that's true. And let me see whether it's true. Maybe there is some ways to do this, and let me see whether the pairs function has such a okay. Oh yeah, it do have an option to only include the subset of the whole data set. And I think the labels is also an optional way to select a subset from the pairs function. Yeah, I think that's, yeah, you can do this within the pairs. I'm not getting a value for my east female variable. How did you get a negative correlation? I'm only getting NA. Oh, I see. So maybe I have changed the span dataset from my side. So I will do this again to make sure I'm the same as you. So for the span dataset, okay. So let me do this again. Okay, so okay, this still work, but if we calculate the correlation, yeah, we have NAs. Yeah, you are correct. So one reason for this is that we have NA values in the dataset, because some of the if we look at the each of female, we can see that we have 3 NA values for this column. So what we can do to avoid this is to remove these NA values from the data. So we can use a function called na.omit. You can use this function to remove the rows which has NA values, and we do the analysis on the cleaned data sets. And that's how we deal with those NA values. And thank you for pointing out that. Yeah, I did the data cleaning before the workshop, so that's why I had different results. Okay, so I will continue. And we can still generate the residual plots and QQ plots. And we can also do box-Cox transformation as we have done before for the simple linear regression models. And here I just show a quick example. So we just plot the model 1. I remember model 1 is the model using all the predictors. So let's see what the plots look like. So we can see that we can still see residual plot. It seems that the trend is flat, but if we look at the QQ plot, it seems that the residuals are far away from the diagonal, which indicates that the data the residuals may not from the normal distribution. And we also see that there is an increasing trend from the scale location plot, which indicates that the residuals do not have the same distribution, and we also see some data points which can be considered as outliers. So we can make very similar conclusions compared to the simple linear regression model. And we can make similar conclusions as well. And we can also generate another model by doing data transformation. So for example, we did log transformation in yesterday's lecture, and we can do the same thing here. So here we have model 5, where the response is log transform suggest retail price. We have done this yesterday, and I guess it still work for today's multiple linear regression, and we can also do the plot. Okay, let's see whether we have some improvement. And okay, press plot model 5, my bad. Okay, you can see that after the log transformation, now the dots are also on the diagonal, and the trend is not so clear for the scale location plot and for the residual versus fitted plots. And we also have, we still have outliers. We still have outliers, the existence of outliers, but the other assumptions are, for the other assumptions, that's much better. So it seems that we can also do similar model transformation for multiple linear regressions. So these can always be very useful techniques. The last thing I like to talk about, which is a special topic for multiple regression, is the multi-collinearity. So it describes whether some of the predictors are correlated. When the predictor variables are correlated among themselves, intercorrelation or collinearity or multi-collinearity among them is said to exist. They are just terms for the same thing. We will discuss the effect of multi-collinearity for 3 different settings. The first setting is uncorrelated predictors variables. So when the predictor variables are uncorrelated, which means that they are totally independent, then if we first regress y on x1, and then we regress y on x2, as the x1 and x2 are independent, so if we regress y on both x1 and x2 and estimate b1 and b2, we will expect to see that the b1 is exactly the same as b1 star, b2 equals to b2 star. So here b1 and b2 are the estimators from simple linear regressions using each of the 2 predictors, and b1 star and b2 star are the estimators from the multiple linear regression with both of the predictors. So this is a case for uncorrelated predictors. So when predictors are uncorrelated, the multiple linear regression can be just considered as a combination of 2 simple linear regression models. But what if the predictors are perfectly correlated? If 2 predictors are perfectly correlated, it means that we can use a linear relationship to describe the relationship between one predictor and another predictor without any errors. So for example, if we say x1 and x2 are perfectly correlated, we can use something like this: x2 equals to 5 plus 0.5 times x1. The key is that there will be no errors. So we can always get the exact value of x2 from the value of x1. In this case, the linear regression model will have infinitely many possible solutions, which fits the model equally well. So we will have not one single solution to the model. And I can show you this by using this example data set. So for example, if we want to predict the model model 1 is the model. Okay, arm span with height using arm span. Okay, this is the original model. However, if we add an extra column, maybe we can add height 2. So for example, if the first is the height in inches and second is the height in centimeters, then there will be 2 heights, but they means the same thing, so they will be perfectly correlated. So if the height 2, let's just do some linear transformation. For example, height 2 is height 1 times 3. And what if we do a linear model which predicts arm span using both height and height 2? Let's see what will happen. Okay, we can see that there will be an error. So we can see that if we only use height to predict, we will get the results of the regression. But if we add the height to add, it is perfectly correlated with height. So we will have errors. So we should pay attention to these cases to make sure that there are no perfectly correlated predictors in our model. Okay, let's go back. So it means that the perfect relation between x1 and x2 does not inhibit our ability to obtain a good fit. And the magnitude of the regression coefficients cannot be interpreted as reflecting the effect of different predictive variables. So you can see that in R, we even cannot get any results from this regression. So we should avoid this case. And the third setting is when we have general effects of multicollinearity, which means that we don't have independent, the predicts are not totally independent, but they are also not perfectly correlated. In this case, usually we still have good fit of the data. In addition, we still have good prediction results. The estimated regression coefficients tend to have large sampling variability when the predictor variables are highly correlated. Okay, I see a question. Okay, no problem. Yeah, I will post today's slides and recording. I will send them to Eloy so that he can post those on the onto the website. And yeah, I think you will receive these. I hope he can post these by end of today's. Okay, no problem. Okay, let's continue. So when several predictors are correlated, the common interpretations of regression coefficients is not applicable anymore. So if regress y on both x1 and x2, it is possible that when individual t-tests are performed, neither beta 1 or beta 2 is significant. However, when the f-test is performed for both beta 1 and beta 2, the results may still be significant. So it means that I can show you what it means using this example. So if we still look at the previous model, the class therefore dataset, I'll show you what it means. So from these regression results, we will see that sorry. From these regression results, we can see that the p-values for city and PG and highway and PG, these two coefficients are all greater than 0.05. So these two coefficients are all not significant. If we interpret these results, it means that if we add city and PG or highway and PG into the model, conditional on the other models, we will not have improvement for the regression model fitting. That's our conclusion. However, if we do the F-test, so as we have done before, I just highlight this. So if we look at these two together, look at city and PG and highway and PG together, you will see that if we do a F-test comparing model 1 and model 4, which means that we want to see whether city and PG and highway and PG do you have improvement to the model, you will see that this time the p-value is much smaller than 0.05. And it means that these two predictors are important. But if we look at the previous results, it seems that these two predictors are not so important. So it means that we have different conclusions from different tests. And this difference comes from the multicollinearity. We know that city and PG and highway and PG, these two variables are highly correlated because conceptually these two things are very similar. Because of the existence of multicollinearity, if we look at each of these two individual predictors, the p-values may be large, but if we look at these two things together, the p-values can be very small. And that's what I say here. So when there do exist multicollinearity, the common interpretations of regression coefficients is not applicable, and we have to pay attention to these issues. Okay, that's what I think that's all for the. Okay, that's all for the multiple linear regression part, and I like to have a 10 minutes break so that. And after this break, I would like to introduce the regularized linear regression, including ridge regression and lasso regression. And make sure that you have the package GLM and ET installed, and you'd better also download the two datasets that I sent to you from the email. And I will stop the recording and we can have a 10 minutes break. Okay, so it seems that we will still use the Zoom link for our first day of workshop as tomorrow's Zoom link. And I think Eloy will be there to host the workshop so that we can still use that link, and he will do the recording. And okay, let's go to our next part. So okay, so far we have introduced the simple linear regression and multiple linear regression, and we can see that in the regression settings, the standard linear model is as follows. So we have y equals to beta 0 plus beta 1 times x1 times plus other predictors until beta p times xp, and we also have a random error called epsilon. It is commonly used to describe the relationship between a response y and a set of variables from x1 to xp. And we have different ways. We have introduced how we use these square to fetch the model, how we minimize the sum of these square to get the estimate of the beta. And do we have any alternative approaches, and and why we need these approaches? We go back to the previous definition of least square. We can see that we use least square because we want to make sure that the predicted value is as similar as the actual value as possible. But sometimes that may not be the only thing we care about. For example, you may care about prediction accuracy and model interpretability. And if we also want to consider these two things, we may change our target, and it will lead to some other models which can fit these requirements. The first thing is prediction accuracy. Provided that the true relationship between the response and the predictor is approximately linear, when we have a large number of samples, when the number of samples n is much larger compared to the number of predictors p, the least square estimate has low variance, and we can safely use the linear regression model, use the least square, using the least square. But if we can look at the third condition first, if the p is greater than n, if we have more predictors compared to the number of samples, in this case, mathematically, there is no longer a unique least square coefficient estimate. And it means that we can perfectly predict the y's for every observations perfectly with no error when the number of predictors is very large. And in this case, we have different solutions to the least squares. So in this case, least square is not the best way to find a good model. And in the middle, when n is not much larger than p, or we say the number of samples is similar to the number of predictors, there will be a lot of variability in the least square fit. And we may have the problem of overfitting in this case. So to summarize, the least square only have best performance when we have a large number of samples. But in reality, in most cases, we do not have so many samples. And in some cases, instead we have large number of predictors which can be considered. And that's why we need to consider some other criteria other than the sum of squares errors, sum of square errors. By constraining or shrinkaging the estimated coefficients, we can often substantially reduce the variance at the cost of a negligible increase in bias, and this can lead to substantial improvements in the accuracy. It says that when we have a large number of predictors, we do not want to use all of them. We want to make most of them have zero coefficients or small coefficients, and which means that we want to shrink the estimated coefficients. And there are two ways to do this shrinkage, and I will introduce these two methods, which are called lasso and ridge regression. When we include another problem about including too many predictors is about the model interpretability. So if we go back to the model, the data set, so we can see that if we have a lot of predictors, so for example, if we look at the highway MPG predictor, although the p-value is quite small, we still have a very large slope. In this case, it still have very large slope. And you can also see that the CDMPG also has a large slope, but horsepower has a small slope. If we include all these predictors in our model, then we will have a, we can say that we can use such a formula to describe the relationship between price and different predictors. For example, price is equal to intercept plus 200 times CDMPG minus 300 times CDMPG, something like this. But how do we interpret these coefficients? Do we really, if these predictors is not so important in this regression, how do we interpret this slope? Do we really believe that a change in the values of CDMPG will have influence on the price conditional on the other predictors? If we do not believe this prediction is important, and it's hard to interpret these coefficients, and this is the problem about the model interpretability. So which says that including such irrelevant variables may lead to unnecessary complexity in the resulting model. And we want to remove these variables so that we can set the corresponding, by setting the corresponding coefficients estimates to 0 and obtain a model that is more easily interpreted. So for example, if we have only a model which only have the horsepower and the cylinders, then we can easily interpret these coefficients because we know that these two are indeed important. But if we add these two actual predictors and we try to interpret this slope when the p-value is already quite large, I think it is hard to say what this slope means because the importance of this predictor itself is questionable. And that's why we want to shrink the number of predictors and shrink their coefficients. So do you have any questions so far? Okay, let's go to the next slide. There are many ways to do the predictor shrinkage. One way is called subset selection. This approach involves identifying a subset of the predictor that we believe to be related to the response, and we then fit a model using these squares on the reduced set of variables. So for example, if we find that by looking at this table, we think that CDMPG and highway MPG are not so important, so we remove these two and fit a model only using horsepower and cylinders. And this is one way to do this, and there is another way called shrinkage. This approach involves fitting a model involving all predictors, so we do not modify the dataset. However, the estimated coefficients are shrunken towards 0 relative to the least square estimates. This shrinkage, also known as regularization, has the effect of reducing variance. Depending on what type of shrinkage is performed, some of the coefficients may be estimated to be exactly 0. Hence, shrinkage method can also perform variable selection. And I would like to introduce two ways to do shrinkage. One is called ridge regression and another is called the lasso regression. Let me first introduce the ridge regression model. Let's recall that when we have p different predictors and we want to fit this least square, solve this least square model by comparing the actual value yi with the predicted value from this linear combination. And we want to minimize this. This is the error, and we want to minimize sum of squared error. This is the sum squared error from linear regression. The ridge regression coefficients estimate are different from these least square estimators. And the difference is that for the ridge regression, other than the sum of squared error, which is this left part, they have another part about the scale of the coefficients. So which we can see that other than the SSE, it also has a part which is lambda times the sigma times the sum of all the square coefficients. So with the existence of this part, we call this a penalty part or a regularization part. And this part means that if a beta is large, it will increase the whole amount to be minimized. And this will encourage a smaller beta, especially when this beta do not have improvement for the SSE. So for example, if we make beta j equal to 0, but the SSE doesn't change a lot, it will encourage that beta to be small or even 0. And that's the intuition for this sum to be minimized. And here you can also see there will be a tuning parameter lambda, and this lambda determines the effect of the penalty for the scale of the coefficients. So we can see that the whole thing has two parts, and you can see a trade-off in this sum. If you want to make the sum squared error to be small, we want the regression result to fit the data well. But if we want to make the penalty part small, we want to shrinkage the estimate of beta j towards 0. So which means that a good model from this optimization will have both small SSE and small betas. And this is a target of the ridge regression. And the lasso is another way to do the regression, and to do the regression with shrinkage or regularization, because there is one limitation for the ridge regression. It is that the ridge regression does have will shrinkage all of the coefficients towards 0, but it will not set any of them exactly to 0. This may not be a problem for prediction accuracy, but it can create a challenge in model interpretation in settings in which the number of variables p is quite large. So for example, the ridge regression, if we use the ridge regression, we can have a smaller estimated coefficients for steady MPG and highway MPG, but these coefficients are still not exactly 0. So if we want to have a better interpretation results, we want that some of the coefficients, some of the predictors that are not linear related to the response condition on the other predictors, we want the coefficient for those to be exactly 0. In that case, we may need to use the lasso regression model. The lasso is a relatively recent alternative to ridge regression that overcomes this advantage. The lasso coefficient comes from the minimization of this sum, this quantity. You can see that the first part is still SSE, and the second part is still lambda times the penalty for the coefficient, but this time we change from the square term into the absolute value. So here we want to minimize the sum of SSE and lambda times the sum of absolute values for all the coefficients. And to solve this, we can get some of the coefficients to be 0. And that's the main advantage of lasso. From if the coefficient for one predictor is exactly 0, it means that by setting it as 0, we do not lose much prediction accuracy, and it means that this variable is so important. So that we can use the lasso regression to select important predictors. For example, we will say that the predictors with 0 coefficient to be not important and the others to be important. So if we compare the target function for the ridge regression and lasso regression, you can see that the lasso and the regression have similar formulations, and the only difference is that the beta j square 10 is the ridge regression penalty has been replaced by the absolute value of beta j in the lasso penalty. In statistical balance, the lasso use an absolute value, which is also called L1 penalty instead of a squared error, which is called L2 penalty, because the L1 norm of a coefficient vector can lead us 0 coefficients from the optimization problem. As with ridge regression, the lasso shrinkage the coefficients estimate towards 0. However, in the case of the lasso, the L2 penalty has the effect of forcing some of the coefficient estimates to be exactly equal to 0, when the tuning parameter is sufficiently large. Hence, the lasso performs variable selection. As a result, models generated from the lasso are generally much easier to interpret than those produced by ridge regression. And as we can do variable selection, you will see that lasso use sparse models, and we only involve part of the variables. Okay, so that's the theoretical part of the lasso and ridge regression. And do you have any questions? Okay, yeah, I think it's better to understand how these models work by looking at the data. And I will look at the CAS04 dataset. And this time I will fit a model which predicts the suggested retail price using all other predictors. So in this case, we have a large number of predictors, so some of them may be not so important. So I will do this myself, and you can follow what I have been doing. So, so first, I would like to look at what's the data look like. So first, let's look at the CAS04 dataset, and we can see that, okay, oh, maybe I will go back to the original dataset to make sure that it's cannot be changed. Okay, because I have modified this dataset previously. Okay, so we can see we want to predict suggest retail price using all other predictors using, okay, we don't want to use dealer cost because I think it is too similar to the original one, so I will use all the other ones. Okay, engine size, cylinders, horsepower, CMPG, high MPG, weight, wheelbase, length, and width. Okay, I will use all the predictors other than dealer cost. Okay, so I'll first make Y to be the response. So it will be the suggest retail price. And we make X to be the matrix which has all the remaining predictors. Okay, so maybe you can do this as dot matrix CAS04 we want to keep the 1, 2, 3, 4. Okay, starting from 5. Okay, 5 to 13. That will be the columns that we would like to include as our predictors. Okay, this is y to our x. And then we can library the GLM and ET, this package, which is needed for the lasso and ridge regression models. We can also make a prediction by using the GLM T. Okay, this function, and x will be the predictor and y will be the response. And here we want to have an actual argument called family. Here we can just make family equals to Gaussian for regular lasso regression, and we also need to know the alpha. So alpha is a tuning parameter. So we use family equals to Gaussian for linear regressions. And alpha, if alpha equals to 1, it means that you are using lasso. And if alpha equals to 0, it means we are using ridge regression. So here we can first try ridge regression, and so that we can make alpha equal to 0. We also have another tuning parameter lambda in this regression model. And from the slides, we can see that the larger the lambda is, the more penalty we add to the coefficients. So it means that if we have a larger lambda, the coefficients will be further shrinkage. So here we can try different lambdas. So first I will use lambda equal to 10 and to see what the results like. And I will also use the coefficient function to get the coefficients. So let me make the model and use coef to calculate the model coefficient. And let's do this. Okay, so from the ridge regression, we can see the coefficient for different predictors, and we can also try using a larger lambda, for example, lambda equal to 1000, and compare the coefficients. And we can see that by adding a larger lambda, all the coefficients are smaller compared to the previous one. So if we compare the engines, look at the engine size predictor, we can see that the coefficient for this is very large when we have a small lambda, but when we have a large lambda, these coefficients become much smaller. And as cylinders and horsepower are important predictors from our intuition, we can see that these two predictors do not have large decrease, a large change in terms of their coefficients. So we can see how a larger coefficients can lead to, how a larger lambda can lead to more shrinked coefficients. And we can also try the lasso model. So this is for ridge regression. And we can also try the lasso regression model. Yeah, we only need to change alpha from 1 to 0 to 1 and repeat the whole thing. And let's look at what the coefficients look like. From the results, we can see that with a very small lambda, the difference between the ridge regression and the lasso regression is quite similar. The coefficients are all in the same scale. But if we use a large lambda, you can see that for the lasso regression, many of them has 0 coefficients. So here dot means 0. So if we don't see a number here, it means that this predictor receives 0 coefficients. And we can see that only cylinders, horsepower, weight, and length, these 2 predictors has non-zero coefficients. And for the others, the coefficients for all of them are exactly equal to 0, including the 2 predicts that we talk about, CTMPG and highway MPG. So these 2 has been removed from the model. And so we can see that if we use a lasso regression model with very large lambda, first, it can help us do the linear regression. We can still have a coefficient for each of the predictors so that we can still get a predicted price for each of the observations. Furthermore, we can know that many of the predictors have 0 coefficients, so that we know that these predictors are not so important, and we can remove them from the model without much loss about accuracy. And so it helps us to do the variable selection, and we can have a good interpretations of the results. And that's how lasso regression works. Okay, and that's an example of using linear regression with shrinkage. And maybe you can also use the class 04 dataset, play with it, and do similar things on your side. And you can let me know once you have finished. Here we can see that in regression with shrinkage, there are 2 important parameters. One is alpha, one is lambda. The alpha indicates how we do the regulation, and lambda means how many penalty we like to give to the coefficients and how much we like to do the shrinkage. The larger lambda is, the more shrinkage we are doing. Okay, I see some of you have done. And is there a typical way to optimize lambda? Yeah, I think you made a very good point, and I will introduce this just after this example. Thank you for your question. Okay, I think most of you have finished, and I will go to our next part. So as some of you have asked, how do we find the base lambda for the regression? Because we can see that the results of the regression is greatly affected by the choice of lambda. So it is very important to find a good way to select the base lambda. And we do this by cross-validation. Cross-validation provides a simple way to tackle this problem. We choose a grid of lambda values and compute the cross-validation error for each value of lambda, and we then select the tuning parameter value for which the cross-validation error is smallest. Finally, the model is refit using all of the available observations and the select value of the tuning parameter. So first, if you are not so familiar with what cross-validation is, I'd like to give a further explanation about this. So cross-validation means that we can fit the model only using part of the original data set. For example, we remove one data point from the data and use the remaining data points to fit the model and make prediction for the missing data point. And we can repeat this procedure multiple times so that we can get the prediction values for all the data points. And then we can see whether the predicted results are good or not. And we can try different lambdas and repeat this cross-validation for all the lambdas and to see what's the means, what lambda gave us the best accuracy from the cross-validation. The reason why cross-validation is important because that when we use linear regression models, actually when we use cross-validation, it means that the predicted value is not, the predicted data point is not used when fitting the model. So that we do not use the data point twice, so that by cross-validation, we can avoid the problem of overfitting, because for each data point, we do not use it for prediction and model fitting at the same time. And that's why cross-validation can give us an idea whether this model is good or not. And we can try different lambdas and do cross-validations and compare the results of cross-validation so that we can compare what's the performance of prediction accuracy for different lambdas. And here is an example of cross-validation accuracies. So here we can see that the x-axis is the scale of lambda from smallest to largest. We try different lambda, and for each lambda, we can calculate the cross-validation mean squared error, which indicates how accurate the prediction is. And then we can find a lambda, which gives us the smallest mean square error, which means that give us the best prediction accuracy from the prediction, from the cross-validation. And we can try this using we can, for our car price prediction problem, we can also try this idea, and I will show you how to do this. So for this data set, we can do, okay, you can use a function called cv.gln. And we can use similar formula to do the cross-validation. And we can use cv.results to save the result of this cv.glm function. Okay, so, and then we can make a plot of this output of the cv.glm function to see what it looks like. So here CV means cross-validation. And from the plot, we can see, so as this plot is very similar to our previous plot. So here we have x-axis meaning the scale of the lambda, and y-axis means the mean squared error for each of lambdas. And a good lambda should have small mean squared error from cross-validation. And here we have two vertical lines from this plot. The first vertical lines will be the lambda, which has the smallest number, sorry, the smallest mean squared error from cross-validation. And the second will be the lambda, which is larger than the original estimation, but it has within the and it gives the prediction accuracy, which is within one standard error of the minimum mean squared error. So you can consider the second vertical line as a more as the larger lambda, which can still give comparatively good mean squared error. So for example, we can compare this and this. We can see that they are much similar, but this lambda is larger so that they can shrinkage more, so that they have better performance in variable selection, but maybe a little worse in terms of prediction accuracy. So if you want to do variable selection and have better interpretability, maybe you should use the second vertical line. But if you only want to minimize the mean square error from cross validation, you can use the first line. Both two are widely used in different analyses. So you can use either in your own analysis to select the base lambda. And you can get the value of these two lambdas by looking at the CV.results. You can use lambda mean as the lambda, which this will give you the lambda which give you smallest mean square error, and the lambda 1 SE will give you this larger lambda which have better performance in variable selection and interpretability. And let's see what these lambdas are. So we can see that 129 and 688 will be the two variables. And we may notice that there will also be another x-axis indicating the number of variables remaining in the model. So we can see that at this side, we still have 7 predictors with non-zero coefficient. And at this side, we have 8, and at this side, we have 1. So it shows if we want to remove 2 predictors, we can stop here. And if we do not want to remove predictors and get the smallest mean squared error, we can go to this part. So this is how we interpret this plot. And another thing is that, so here you just remember these two values, 130 and 688. And if you run the whole things again and look at these numbers again, you can see that these numbers are different. So it becomes 200 and it becomes more than 700. And we go back to the plots, we can see that this time for the lambda, which have received the smallest mean square error, this time it removes one predictor from all the predictors, and this only gives us, and this lambda is larger than the previous lambda by running the same code. And if we run it again, we can see that the results further changes, and we have this time the smallest, the first lambda become 42, and you can see that this minimum comes from this side. So from these results, we can see that the output of this is not fixed, even by running the same code. The reason for this is that, as we have just said, we need to do cross-validation to select the base lambda. And in cross-validation, we want to random sampling several samples to be left out and use the remaining samples to predict the Y values for those left samples. And this part has the process of sampling, of random sampling, which means that if we have different random sampling results for the cross-validation, the whole procedure will be different, and the resulting lambda will also be different. So this we need to keep this in mind if we want to use this function to select the base lambda. And one way to avoid the randomness is to set a random seed to make sure that all the polling analyses are reproducible. For example, if we can add a function called set.seed, and this is just a random number I randomly pick, and after we set the seed, all the random things in the whole procedure will be fixed given this random seed, so that we can make sure that all the results are reproducible. So we can see that if we run once, we have 15 and 688, and if we run it again, we still have 15 and 688. So that's why we can use, that's how we can use random seed, fixed random seed to make our results totally reproducible. Say we are doing research, and for example, you are doing a cross-class project, and you want to reproduce your results in the future, it is needed to set this random seed before using this function to make sure that if you run this function again, you will get the exactly the same results as you did previously. So we need to set the random seed to make results reproducible. We will also see that compared to the lambda mean, which has large variance, the lambda 1SE has smaller variance, and this why sometimes people may prefer using this larger lambda for lasso regression, because it is more stable from cross-validation, and it will also give us better interpretability. In practice, I think there are people which are use first one and people use second one, so both make sense, and it's safe to use both in your own analysis in the future. Okay, and I think that's my idea about how to use these CV.grmnet, this function to do parameter tuning to select the base lambda from cross-validation. And the next thing is, how can we use this lambda? I think it's just very straightforward. We can just use this as our, for example, you would like to use the larger lambda, which is the lambda 1SE, and we can fit this model using this lambda and look at the coefficients. So this will be the whole procedure of lasso regression or ridge regression. So we have two steps. First, select the base lambda, and then run the model using the selected lambda. And then we can look at the coefficients to do variable selection and do interpretations. We can see that in this case, we have removed the two variables, engine size and high weight MPG. So because these two are not so important compared to the other predictors, and we also get the coefficients of the other predictors after regularization. So that's the whole procedure of the lasso regression. Okay, so I think we can take another break, and we can also use this time to reproduce these results on your side. And I think if we have the same version of R, we will get the same, exactly the same results for the coefficients if we also set the seed equal to 1, 2, 3. And you can tell me once you have finished, and I think we can take a 10 minutes break here. I will pause the recording. Okay, let's continue, and I'll go to our last part. So in this part, I will introduce generalized linear regression models, and it will include logistic regression, Poisson regression, and negative binomial regressions. So I think these regression models will be very useful for different areas of analysis. So let me first introduce the background of logistic regression. So suppose we want to predict whether a given individual will vote yes or no for the ith individual. And then we can have okay, for the ith individual, we can let yi equal to 0 if he or she voted no, and let yi equal to 1 if he or she voted yes. So we can see that as the results will be yes or no for each of the individual, then we will have the binary outcomes. So response will be binary if you want to predict yi. So in our previous linear regression models, the response values can be values which can vary from, can take the range from small number to large number. For example, if we look at the suggested retail price, the example, the price have very large range. However, in this case, the response can only take two values, either 0 or 1. So it means that if we want to make this prediction, our previous model cannot be used. And from our intuition, there are still many predictors that can be used to make this prediction. For example, age, education, and salary, these are factors that can affect the results of the vote. And these predictors can be either numerical or categorical. For example, the age and salary will be numerical and education will be categorical. We can use all these predictors, want to use all these predictors to predict the results of the vote. And how can we do this? You have considered this structure, this random structure. We can assume that the response yi for the ith individual follows the Bernoulli distribution with Bernoulli parameter equals to pi I. So here, if you are not so familiar with Bernoulli distribution, the Bernoulli distribution with parameter pi I will has pi I probability to be 1 and 1 minus pi I probability to be 0. So it will only take two values, 0 or 1, which is the same as our response, either 0 or 1. And the key part of this Bernoulli distribution is the parameter pi I, which is the probability of getting a 1. The expectation of this random variable will be pi I, and the variance will be pi I times 1 minus pi from its definition. If you use some mathematical calculation to do this, we will have these results. So this gives us an intuition that if we want the yi's from the Bernoulli distribution with pi I as the parameter, we can somehow use a linear relationship to describe the relationship between yi and the predictors. In multiple linear regression, we can write yi as the sum of beta k times xik, k from 0 to p minus 1 plus epsilon I, where epsilon I is a random arrow. This is the formula for multiple linear regression, and can we use similar structure to describe the pi I here? The first intuition is that maybe we can use this to describe pi I. We can make pi I, which takes values from 0 to 1, to be a linear combination of beta k, betas, and x, and the predictors. So we can, this is our first case. So, however, there is a problem with this formulation, because in this case, the pi I should be values from 0 to 1 from the definition of a Bernoulli distribution. But actually, this linear combination can take values from negative infinity to positive infinity. So for example, if we have very small x or very large x, we may have very large predicted value from this formula. And if pi only takes values from 0 to 1, it does not meet our requirement. So we may propose our second model. So this is our second proposal. So in this one, we consider whether we can change a value from 0 to 1 into a value which takes a value from larger range. So this time we make the response to be pi I over 1 minus pi, which is the probability of yi equals to 1 over the probability that yi equal to 0. So as pi I can be from 0 to 1, if pi I equals to 0, this value will be, this left part will be 0. And if y equals to, if pi equals to 1, then this part will be infinity. And this will be a monotone function for pi I. So we can see that for different pi i's, the left part will take values from 0 to infinity. Okay, so in this way, we have successfully changed the pi I, changed the range of pi from 0 to 1 into a range from 0 to infinity. So we can, in this case, I think this is already a much more reasonable response. So we can use, maybe we can use this linear combination to describe this ratio of proportions. But it is still perfect, not perfect, because it is from 0 to infinity, but we want the range to be negative infinity to infinity. So that's why we finally propose our final model as follows. Here we take the log of this ratio. If we take the log, if pi I is small, if pi is equal to 0, then it will be log 0, which is negative infinity. And if pi I equals to 1, then this part will be infinity, and log this part is also infinity. So that by taking log, we have generate a response which takes values from negative infinity to positive infinity. And this is the desired range of the response of a linear regression model. And we can now propose it as our final model. And this is the formula for logistic regression. So for each response, I, the probability, we model the probability of that this yi equals to 1 over the probability that yi equal to 0. We model this ratio using this linear combination. And we define this function log of pi I over 1 minus pi I. We name it as logit function. This is just a name for this function. And we can see that this function is monotone increasing function. And if pi I equals to 0.5, then the ratio is 1 and log 1 equal to 0. So it means that if this ratio is, so if logit pi I is negative, it means that this ratio is smaller than 1. It means that the pi I is smaller than 1 over 2. And conversely, if the logit function is positive, then the pi I is greater than 0.5. And the beta j will measure the increase in logit function when xij increase. So for example, if we think the increase in one predictor will increase the probability that the individual vote yes, then the beta k will be positive because, and you can see that if beta k is positive, a larger x if beta k is positive, and it means that if we have a larger xik, then the right part will be larger and the probability will be larger, and the person will have a larger probability to vote yes. So that's the intuition for this formula. And okay, so this is the formula for the logistic regression. And do you have any questions regarding the theory part? Okay, if not, we can continue to the implementation part of this model. So if we go back to the class 04 dataset, and we can see that most cars have either 6 or 4 cylinders, and we can validate this by looking at the data. So let's look at the class 04 dataset. We can use the table function to generate a table of a specific vector. For example, here we are interested in the number of cylinders for the cars, and we can see that among these about 200 cars, 91 of them has 4 cylinders and 99 of them has 6 cylinders. So that these are 2 are the majority. So maybe we are interested in these 2 parts, and we want to see whether we can use other predictors to predict whether this car has 6 or 4 cylinders. So you can see that the response will be whether it has 6 or 4, and it will be a binary outcome. So maybe we can use logistic regression for this task. So first, we generate a subset of the dataset that has 4 or 6 cylinders. And we can do this by using the subset function. So here we make cars therefore sub as the sub dataset, which only have cars that have either 4 or 6 cylinders, because they are the majority and we are only interested in those cars. So here we use the subset function, and this will have 2 arguments. The first argument is the name of the dataset, and second will be a logical expression. So whether the cylinder equals to 4 or cylinder equals to 6. So, and this will give you a subset. And then we can see we can verify whether we get the correct we can see whether we can get the correct results by looking at the table of the second subset. So we can see that after this, we have removed all the cars whose cylinders are not 4 or 5, 4 or 6, and we only have 190 cars. And all the cylinders of these cars are either 4 or 6. And then we want to predict the number of cylinders from the predictors. So for example, we want to use horsepower, highway MPG, and city MPG, these 3 predictors to make the prediction, to predict whether cylinders, the number of cylinders is good or not, is 4 or not. So first we can add an extra vector, an extra column to this dataset, and we can name it as cylinder 6 to indicate whether this car has 6 cylinders or not. So we make cylinder 6 equal to whether the number of cylinders equals to 6 or not. And we can also look at the table of this column. So we can see that 99 of them will be true and 91 of them will be false. And then we can do the prediction. And to do the prediction, we need to use a function called GLM, which is short for generalized linear models. And in GLM, we will first have a formula, and this formula will be similar to our linear regression models. We want to predict cylinder 6 using horsepower, city MPG, and highway MPG. And data equals to cars, therefore sub. And we want to use logistic regression. So we will have an actual argument called family, and we'll take here we will make family equals to binomial, and we'll have a link function, logit. Okay, so we can save it as model 1, and we can have a summary of this model as we did for the linear regression models to interpret the results. So from the outputs, we can see that we can find a linear relationship between the logit function and these predictors. All of them are significant, including horsepower, city MPG, and highway MPG. And we can look at the predicted probability for each of the observations by looking at the fitted value of the model. So we can look at the fitted value of and we can see that these values are predicted probability for each of the observations ranging from 0 to 1. And this will be the probability that this car has 6 cylinders. So maybe you can repeat these procedures on your side and to see whether you can do these logistic regressions successfully. So we have several steps. First, we need to generate a subset of the data set, and then we need to add an extra column indicating the whether the number of cylinders is 6 or not. And then we use 3 predictors to predict that binary outcome from using logistic regression. And finally, we can look at the coefficient and their p-values. This will be the whole procedure for the logistic regression. And within the GRM function, the key part will be the family argument. If we are using logistic regression, we should set it as binomial logit. This is how we do logistic regression. And for other generalized linear models, you will change this argument. And yeah, you can try it on your side and let me know if you have finished. And you can also ask me if you have any questions. So just to confirm, for logistic regression, you would use GLM and not GLM NET. Yes, that's correct. I will use GLM. So yeah, I think you made a very good point. We can also use GLM and NET to run penalized logistic regression, which means that we also run logistic regression, but similar to lasso or ridge regression, we add an extra penalty 10 to shrink the coefficients. And in that case, you can run, if you want to do that shrinkage, you can also use GLM and NET to do that shrinkage. And yes, it has its own ways to do this. And if you're interested in this, you can look at the document for GMNT, and I'm pretty sure that they will have show you how to do this. And here I will only introduce regular logistic regression and without penalty. So I use the GLM function. Please let me know if you have finished so that we can go to the next part. I may wait for one more minute. Okay, so maybe I can give you another task, the final task, so that you can, so if for those of you have finished, you can go to the last question. So what is the prediction accuracy for this logistic regression? So I will not show you how to do this. Maybe you can calculate the accuracy yourself, and you can type your answer in the chat box once you have finished. So what's the prediction accuracy? So for each car, we will know that whether it has 6 or 4 cylinders. And we also have the predicted value from the logistic regression model, so that we can, which is this. So one way to make decisions for each of the individuals that we can compare predicted, we can make the cars which has probabilities greater than 0.05 as the cars predicted to be 6 cylinders, because it has larger probability to be 6 cylinders than 4 cylinders, because the probability is greater than 0.05. And then we can predict the cars whose probability is smaller than 0.05 as 4 cylinders. It is one way to make decision. And then we can compare the predicted cylinders with the actual cylinders to see whether we make correct prediction for each of the individuals, for each of the cars. And then we can compare the predicted value with the actual value, so that we can calculate the accuracy. So maybe we can further work on this to see how to calculate the prediction accuracy. So maybe I can give you 3 minutes for this task. And if you have not finished the previous part, you can still work on the previous part. And if you have finished, you can try to calculate the prediction accuracy. And we can see whether you have the same results about the accuracy. Okay, have you finished? So you have finished the calculation accuracy. Maybe you can type your results in the chat box. Or even though I think I can introduce it myself. So here we can see we have the fitted values from the logistic regression model, and then we can also compare the fitted probability with 0.5. So that here I define a new vector called predicted, which is whether this probability is greater than 0.5. And then we can compare the predicted value with the actual value, which is the cylinder's 6 variable from the data that we had defined. And then we can see whether these two are the same. If it's the same, it means that the predicted value is the same as the actual value. And then we can calculate the mean of this to get the accuracy. So it will be 95%. So that we have a correct prediction results for 95% of the cars, so which is quite high. So it means that this logistic regression model have very good performance in predicting the number of cylinders from the 3 predictors provided. So here I use mean because we can, this mean means that we calculate the total number of correct predictions and divide that number by the total number of cars. And that will be how we calculate the accuracy. So it's just taking a mean of all the values over 0.05 and comparing with cylinders 6, right? It's not exactly. So first, I get the predicted value for, could you also use ANOVA to check the prediction? Yes, you can use ANOVA. So you make a very good point. ANOVA model web. So you can do this. So we can also use ANOVA to get to do the F-test. And we can also do a model with a smaller number of, for example, only using false power, and do a logistic regression and compare model 1 and model 2. It still works, and we can see whether what's the change in the degree of freedom, and what's the difference in the given change of the demons is explained. Here they don't offer us a p-value. And I think if you want to get a p-value, I guess you may need a ANOVA function provided by the MASS. Yes, there is another function called ANOVA from the MASS package, and this will give you ANOVA, which can be used for logistic regression. Okay, and come back to the main question. Sorry that I left this topic. So actually, so here what I did is first I get the predicted value whether this car has 6 cylinders or not. So if we look at this predictor variable, there will be all true or false numbers. True means that we predict this car to be 6 cylinders, and false means that we predict it to be 4 cylinders. And then we compare this with the original, the true cylinder vector, and this will also be a true or false vector. So this time it's true means that the predicted number of cylinder is the same as the actual number of cylinder, and it is false If it is false, it means that the predicted number of cylinders is not the same as actual number of cylinders. And we can see that most of these are true because we can correctly predict most of the cars. For most of the cars, the predicted number of cylinders is the same as the actual number of cylinders. And then we can take the average of this vector to calculate the accuracy. I guess would you always say fitted values greater than 0.05? So if we are doing a binary prediction, it's true. So if we are doing binary prediction, we always use 0.05 as threshold. So we can, if the fitted value is greater than 0.05, it means that we predict the response to be true in this for the like binary response. We predict it as true if the probability is greater than 0.05. And we predict it to be false if the probability is smaller than 0.05. Okay, thank you for the question. And go back to the ANOVA one. So while using the ANOVA model one along with the results, I am also getting the following warning message. Fitted probability numerically 0 or 1 occurred. Yeah, it happens. So if we go back to the fitted value vector, and we look at the minimum of this. So you can see the minimum is very, very small, and it is close to 0, and we go to maximum, and we can see we have large maximum values. So I guess this warning message comes from this small number, which is close to 0, and it will be regarded as 0 in R in some part of the calculation. In this case, if the probability is 0, if we go back to the formula of this, if pi I is 0, then this function will be log 0, which is not correct, because log 0 is negative infinity, and this will cause errors in the calculations. And that's why we don't really get 0 probabilities or 1 probabilities from the logistic regression. And that value, which is very close to 0, was calculated as 0 in some part of the calculation, and that 0 will lead to some errors, because here we will sometimes need to calculate the ratios in some of the part of the calculation, and this will lead to errors, and that's how this warning comes from. I mean, this warning will exist when we have some very small or very large probabilities, but it will not harm the results. Okay, I think we only have 15 minutes for the last part, the Poisson regression and mixing binomial regression. Maybe I will not go to the details of these two regression models, and I will leave them to tomorrow's workshop. So let's first go to the Poisson regression model. So if you still remember, I introduced example in yesterday's workshop, the DEG identification from RNA-seq data. So in this case, we have samples from 2 conditions. For each gene, we want to see whether the counts is affected by the condition. So in this case, the number of counts will be the response, and the condition can be the predictor. If the gene is a DE gene, it means that we can use condition as a predictor and use that predictor to successfully predict the number of counts. And if it is not DE gene, it means that the difference in number of counts is totally from random noise, and the condition is not a significant predictor. I introduced this problem yesterday, and let's come back to this problem to see, can we use linear regression to solve this problem? So here our predictor will be the condition. So it will be a binary predictor. It is either 0 or 1. However, if we look at the response, we will see that we may not, maybe we cannot use the linear models that we used before, because the read counts are non-negative integers from its biological meaning. The reads, the counts is the number of reads that can be located into the gene region. So it is a number of reads, and that number should be non-negative and be integers. However, in the previous linear regression problems, the response can take values from negative infinity to positive infinity. You have solved this inconsistency in logistic regression by assuming that the response comes from a Bernoulli distribution so that the yi can take values from 0 to 1. Can we use similar techniques to make the response to be non-negative integers so that we can use similar models to model the relationship between the condition and the number of counts, the number of reads. So, and here is how we solve this. So here we assume that the number of reads comes from a Poisson distribution with parameter lambda. So if you are not so familiar with the Poisson distribution, the random variable from a Poisson distribution is always non-negative and integers. And the one important property of Poisson distribution is that the variance and expectation of this distribution is exactly the same, and they are both equal to lambda. We can use RPOIS, this function, to generate Poisson random variables with different parameters and look at what they look like, what they're like if you are not so familiar with this distribution, and let's take a look. So let's go to the and we can generate Poisson random variables. For example, we generate 10 Poisson random variables and make lambda equals to 5. So that the variance and mean will both be 5. And let's look at what data look like. So you can see that these values are all non-negative integers, and the variance and mean are all equal to 5. And if we change lambda, we will get different results. So this is just to give you intuition what Poisson distribution looks like and why we think it is reasonable to describe the read counts in the D analysis, because they are all non-negative integers. So far we have found the correct distribution to describe the response. And the next is to find the link function between the response and the predictors. So if you still remember, in logistic regression, we use the logit link, which means that we describe the pi I over 1 minus pi I and taking the log, which is logit function, and use linear combination of beta and x to describe that logit function. In this case, we also want to make sure that the range of the linear combination is the same as the range that we desire. Intuitively, we want to use these linear combinations to describe lambda I. However, similar to our previous problem that we had in logistic regression, we know that the parameters for though just for Poisson distribution should be non-negative. However, this linear combination can take values from negative infinity to positive infinity, so that we also need to do some transformations on the lambda. And that's why we take log of the lambda. So it means that in the Poisson regression, we assume that the log of lambda can be expressed as the linear combination of the predictors. So we can use a linear model, multiple linear model to predict log lambda using the predictors. And yeah, and I think we have introduced similar formats in yesterday's workshop, where we introduced that if we want to do some data transformations on the y's, we also have similar patterns. So if we go back to this, we know that the expectation yi is lambda, and in this case, if we think that the log of expectation of y is equals to this random combination, we will see that the expectation of yi will be the exponential of this linear combination. So I think that may answer that the question by Prashansa. Yes, she asked me a question about how we can use linear model to describe the linear trend. Sorry, to
Yes,
describe
thank
the
you.
exponential trend, and we can see that if we use the Poisson regression, we can see that the expectation of y, which is lambda I, log of that is this linear format, so that expectation of yi will be exponential of this linear format. And if you recall, in yesterday's workshop, we talked about data transformation. So if we take the log transformation of the y, we also have that log yi follows the comes from a linear combination of the predictors. And in that case, we also have yi can be expressed as exponential of this linear model expression. And we can also see that in this case, we also have expectation of yi having the same formula as the Poisson distribution. So that we can see that these two things are quite similar. And what's the difference between doing log transformation on y, between that data transformation and Poisson regression? The difference comes from the values of yi's. If we do data transformation, the yi's can take any value. But if we do Poisson regression, the yi's can only be non-negative integers. And the randomness comes from the Poisson distribution. And that's the main difference between these two models. Okay, I'm not sure whether we have enough time for this, but I will try to finish this. So we will look at the simulcount POIS dataset. And this will be a matrix where each row is a biological sample and each column is a gene. And the entries will be the read counts. We would like to do a Poisson regression for the first gene, and we can calculate the p-value of the coefficients. Let's see. I think I will try to finish this for today, and I will leave the remaining part for tomorrow. So let's look at the dataset first. So let's read the table. So we use the function called read.table to read the txt file, and this will be the simulpos.txt. Oh, so let me check whether I send you the txt file or CSV file. Okay, I send you the txt file. So I made them. So I should use the txt file. Dropbox. That will be the directory of the file. Okay. So we can see that this is a count matrix, and I want to use this matrix to mimic the real gene expression matrix. So here we only have 200 genes, and we name it as simu count. Yeah, I generate this data set from simulation, so it is not a real data set. And then we want to look at the first gene so that we can first get the count of that gene. So we make count a vector, count equals to the first column of that matrix, and we make condition as so if we look at the row, we can look at the simu count matrix, we can see that we have 5 treatment samples and 5 control samples. So if we want to use condition as a predictor, then and we can make the first 5 as 1 and the last 5 as 0. So we can generate such a condition vector. So the first 5 are treat, and the last 5 are control. And that will be our predictor. So let me show you what the condition vector is like and what the count vector is like. So the count vector is 10 integers, and the condition vector is 10 conditions. And then we can combine these as a data set called d.data to do D analysis. And it is a data frame which has these 2 vectors, count and condition. And then we can use Poisson regression to solve the regression model. And we can use similar format as logistic regression. So we still use the GIM function, and we want to predict condition, sorry, predict count using condition. And we want to use the d.data dataset, and we make the family Poisson. Okay, this is how we do the Poisson regression. We still use the GIM function, and we just change the family from binomial into Poisson, and log will be the link function. And then we can also use summary function to get the interpretations. And you can see that the condition do have effect on the number of counts. And we can see that the p-value of this is quite small. So that for this gene, the condition can be can play an important role in prediction of the read count. And that's the conclusion we can make from this Poisson regression. And you can also repeat this on your side. And I think that will be end of today's workshop, and I will cover the remaining part for tomorrow. And for tomorrow, we will also use the link for yesterday's, the same link as yesterday's link. And for tomorrow, I will first finish the Poisson regression and negative binomial regression parts, and I will also introduce how to solve the problem of multiple testing. Yeah, you can try to finish this, and I will stop the recording here.